Also. Thank you, Cécile.
Yes, so I'm not as tall as Marianne. So I'm going to talk about really about the topic of this workshop, incentive contracts to foster the ecological transition. And it's going to be mostly based on joint work with Yann Reynaud, who's here, and Marc Reynaud, who's here. And it's a theoretical approach. So I want to warn you, there are going to be equations, but you don't need to understand them. It's just for decoration. So this is a theoretical study that is informed on the work that Marianne mentioned before, but tries to. So it's going to be highly stylized, but it tries at identifying key points that may be obstacles to the ecological transition. And very clearly, there are now many best management practices that exist, and agronomists tend to believe that they are effective, at least in a number of contexts, but farmers don't adopt them. So we have a standard problem of innovation adoption. They don't want to adopt. There are many barriers to adoption. This can be financial, behavioral, etc., etc. But here we are going to focus on the one that is probably an essential one, which is risk, uncertainty. When you adopt a new practice, you don't know if it's going to work or not, especially when it's something such as best management practices, where you need to really fine-tune what you're doing, in most cases, to the context and the situation. It's very easy to spray. Well, it's easy to spray pesticides. It's much more difficult to use biocontrol or other methods. So this is something that involves more risk and learning. And we have decision support systems that are really helpful in this because they can help and guide the farmers and tell them what to do at which time. But they involve themselves as a source of risk. They are a source of risk because, again, to begin with, it's a new product, it's a new tool, and we don't know its quality. By quality, between quotes, I mean, is it going to work in my own context, given my soil type and given the climate I'm facing and the type of, etc., all the things that are specific to my context. And also, is it a good tool, or is it something that has been well marketed but is just not efficient? So from the point of view of farmers, these tools are also risky in the sense that we don't really know if they're good or not. And this is what I'm going to focus on. So this is a new source of risk. Because it's a new source of risk, there's a potential for insurance to play a role. And here what we're studying are the benefits and the limitations of a specific green crop insurance, like the one Marianne presented, to foster experimentation. Oops, sorry, I went the wrong way. Oops. So we study a theoretical model, as I mentioned, where in fact you learn along the way about the quality of a decision support system that is structured in order to reduce pesticide treatments. So it's really a green system that helps you reduce your treatments or follow a best management practice, but you don't know if it's good or not. Because, as I mentioned, because these best management practices require more adjustment to the local condition, it's very difficult to assess the quality of the tool from examples of some other part of the country made by someone else in different conditions. So the implicit assumption is that you cannot assess the quality of the recommendations if you don't try them. And that may be correct or it may be incorrect, but we believe that it can be a general belief that many farmers share. But if they haven't seen it tested in similar conditions to them, and ideally on their farm, then they're not going to be confident about the quality of this tool. So here, insurance can really be a facilitator because it helps cover the risk of trying this tool. So it helps learning because you can be protected by the insurance when you experiment with this new tool and learn along the way whether it's good or not for you. And so this is, smarter. In fact, because of the agricultural timelines, what we're going to see is that learning will be slow and it can be inefficient. And so there's no guarantee that insurance will solve all problems. So insurance is a potential very good instrument, but it has limitations that are not due to insurance itself, but that are due to the agricultural context. And in this story, other effects are going to matter, which means that what happens in the first year is going to have a strong impact on what happens next. Okay, so again, there's not going to be anything very fancy about this, but I think it can help structure what we've been talking about, so I hope it helps. Before moving into the details, I would like to go back to clarification about information, because this is really something we've been mentioning here. We have the climatic data, which is very useful to build the models, to make predictions, and for insurers, at least for climatic insurance, but also for pest insurance, because we know that there is a correlation. The more rainfall you have, the more likely it is that you have mildew, for instance. So we have lots of correlations between them. And this is going to be probably an underlying risk in insurance contracts, because it's very likely that any pest insurance contract that is provided also is also associated to a climatic insurance contract. So there is this underlying climatic risk that is going to occur with some risks that are common and others that are more idiosyncratic, like hail. The pest-related data is much more difficult to observe and much more difficult to put in a contract. So this is something that was mentioned this morning. It's relatively easy to have an index or an insurance contract that is based on climatic data because we have reliable sources. When it's pest, the damages come from a conjunction of factors. It may be much more difficult to evaluate whether there are damages or not, and whether damages are due to this pest or that one, or to pest at all. So it can be much more difficult to put it in an insurance contract as a clause, and there may be more judicial uncertainty, which is really something that was mentioned this morning. And then what we are looking at here, the expert recommendations, whether they are digital or human-based, but here we're going to focus on digital recommendations, they add another layer of uncertainty because they're based on predictions. You should behave that way, so you should spray or you should not spray that week. You can wait for 2 more weeks without spraying. This recommendation is based on a treatment of all the data available with a model. So we have a model, an agronomic model of the world, which says that under these conditions, I should do this or that. But of course, the quality of the underlying model is something that is essential to the quality of the tool. And this is something that is unknown or badly known, at least to farmers. It may be well known to the experts, but it's not necessarily well known to the farmers. And also the fact that there is climatic change means that our models of how the world works need to be adjusted. And so there is model uncertainty, which is, in fact, what we are focusing on here. It's the fact that we don't really know what's happening. So the framework we are looking at is the following. We have, I hope it's clear. So we have data related to the environment, well, data coming from the environment and the climate. That gives us some information on what is called theta, which is just, is it a good year or a bad year? Is it a situation where I should spray a lot or not? Then the DSS processes this. This is a red arrow. It's processing, the quality of which is unknown, and it gives recommendation. Quality is going to be measured by Q, like quality. It gives recommendations. And the farmer can follow or not the recommendations. If it doesn't follow the recommendations, there's no learning about the tool. We don't know if it's a good tool or not. If it follows the recommendations, it means it experiments with the tool, it chooses to try it, then some learning is generated because we can see if the tool was good or not. The farmer can learn about this, but also, this is the dotted arrow, we can improve the model, which is, I think, something that Giuseppe mentioned, maybe not exactly the same thing, but the fact that you get data from the farmers who subscribe to your insurance policy, and this data is helpful in order to at least improve forecasts, at the very least. So it's helpful for insurers, at least. and it can be helpful in improving the model that is being used. So we want to induce experimentation, even if in some cases it's going to end up with a negative result. Like, okay, no, the tool is not good, that can happen. Okay. So a farmer can either cultivate as usual, that is not follow the recommendations, or follow the recommendations. The source of risk here is the fact that the DSS can fail. A failure of the DSS means it doesn't identify a situation where you should treat. This DSS, remember, it's a green DSS, it's trying to help you minimize sprayings. So errors will tend to be not treat enough, okay? Because it's constructed in that way. And so this happens with some probability, it's going to fail with some probability, and the fact that you don't know whether this tool is good is reflected in the fact that you don't know this probability. So there is a probability of failure, okay, everybody can fail, but you can be good and fail very little, or you can be bad and fail often. And that is going to be measured by 1 minus Q, that's probability of failure. So Q is the probability of being correct, so Q is quality. The larger Q, the better that is. You have better quality. But this is unknown at first. You don't know if the DSS is going to fail often or not, so this is my crucial variable. And learning is going to be slow, because we're considering a context of pest management. For pest management, it's very difficult to try a practice on a very small plot, or you cannot fragment plots. If you want to try new seeds, new varieties, it's usually very easy. Sometimes you need specific machineries, but most of the time you can try it on a piece of land and do as usual on the remainder. Here, it's difficult because you might have contagion, and in addition, there is a fixed cost, which is not so much buying the DSS as optimizing labor. Because if you want to follow the DSS, you're going to have to change you're going to have to change the way you treat. So instead of having a very regular schedule where your agricultural workers come to spray on Monday and Wednesday and etc. It's very regular and it's all scheduled, and you have another DSS which is telling you exactly what to do. Yeah, it's going to be adjusted more or less in real time, depending on the data you get, depending on the climatic data and on what pressure measures tell you. So it's going to be much more complicated, more costly, and this is a cost that shouldn't be underestimated. So I'm not going to model this, but this means that you cannot try on a very, very small, you cannot infinitely fraction your experimentation plot. You're obliged to try on a sufficiently large scale, which means it's a real risk. It's not a small risk. It's not going to be a small risk. So don't worry about the equations. This is just nature is modeled as an actor who is going to choose whether it's a good year or bad year, high pest pressure or low pest pressure. The low pest pressure is at the bottom. In that case, that's 0, 0 means you need 0 spraying. That's, of course, an approximation. You don't need much spraying. The DSS is always correct in that situation because it always wants to minimize sprays. And if you follow the DSS, everything is fine and you're saving on unnecessary pesticides. Again, don't worry about the expressions. At the top, you have situations where there is high pest pressure and you would want to treat. So this is why you have the capital letter T. You would like to treat, but then the DSS may make a mistake. With probability Q, it's going to be correct, but with probability 1 minus Q, it's incorrect. And it perceives the situation as not requiring spraying, so requiring 0 sprays. The dotted line in red here is what we use in game theory to represent the fact that some actor doesn't know exactly where it is. That is, when you're making a decision, you don't know exactly everything that happens before. You don't know exactly if you're in a situation in which DSS is recommending you not to treat and it's correct because nature has drawn a good situation, or if you're in the other situation in which the DSS is recommending not to treat, but that's because there's a failure. So you don't know, you have to make a decision and there's uncertainty. And here in red, you have the risk of making losses, and in blue, you have the benefit of saving on pesticides. Of course, if the cost of pesticides is very, very small, it's not very attractive to make the risk. But the key point is that everything depends on this Q, which is quality of the DSS. If it's a good DSS, it's very unlikely that you're going to end up in a red situation in which you're making losses. But you need to experiment. Okay, so precision can be high or low. I'm simplifying the model. And what happens is that you're going to very intuitively follow the DSS if and only if you believe that quality is high enough. So you have a mathematical expression here, but what matters is just this. If you believe that it's high enough, that's okay. The mathematical expression is only helpful for us to derive implications. The most important point here is that, in fact, in order to model learning, we use Bayesian updating. So you use Bayes' rule to update your beliefs depending on what you observe. If I observe a success, I'm going to change my belief. If I observe a success, etc. What happens here, and it's also something that was mentioned this morning, is that low past pressure situations are not very informative. In good years, everything works. Okay, so you don't learn anything. You learn only when you are in a bad year, so with probability P. So you learn only when it's a bad year, and you learn only if you have decided to follow the DSS, and you learn only if the DSS is proven to be incorrect in some sense. This is where you learn that the DSS was bad. So learning is going to be slow, and that is really what is very important. Insurance is going to help. Again, you don't everything about the equations is not important. What matters is just that insurance reduces your losses when you make losses. So if the DSS is incorrect, you're not going to lose as much. So very clearly, you're going to be more willing to experiment. And that means you're going to be willing to experiment for more pessimistic beliefs, worse beliefs. Okay. So insurance is good because it helps experimentation, but it's not necessarily enough because we have this thing that learning is going to be very slow. And because of this, and because of the specificity of Bayesian updating, which represents anyway what we know about the brain, so that's good, other effects are going to be very important. So this is it. So we cannot apply a law of large numbers, which is something very important because usually when we do analysis of situations like this with risk about data or pests or whatever, we tend to assume that there is an underlying distribution of the risk that is known to all parties. And we also assume that people are rational, so they're going to converge towards a true distribution if they don't know it to begin with. And we apply a law of large numbers, which is, okay, if we experiment, we're going to converge and have beliefs that correspond to true distribution. But here, this is not possible because you only learn potentially once per cultivation period. You follow the protocol and it worked or not. It has taken you 3 months, and you have to wait until the next year until you get another observation. So you have very few observations. After 3 years, you have at most 3 observations. And some are not informative because it was a good year and everything would have worked anyway. So you're going to learn very slowly, and every observation is going to have a lot of weight in your beliefs. So if you have a first failure, it's going to weigh a lot. And also there is an asymmetry, and this is where Bayesian updating works like the brain, which is that we learn more from rare occurrences. If everything happens as expected, you don't change your beliefs. You change your beliefs when something happens that is unexpected, which is also the way we treat information in our brains. So this means that here, what should be rare should be failures. We expect the DSS to be sufficiently good, so we expect failures to be rare compared to successes. So failures are going to change our beliefs much more than successes. There is an asymmetry in the learning system, which is, we are going to be, so we are, everything is wired to make us pessimistic in some sense, and to put much more weight on the failures than on the successes. And there's going to be a strong path dependence. I've plotted below just an example that is not based on real data or anything, but just on the left, you have 2 successes first, and then 2 failures, and different configurations of risks. What matters is just that if you have successes first, you see that your beliefs, what is plotted is a belief. Your belief is about the quality increases a little, but then when you have a failure, it drops very sharply. And the red line that is here is supposed to be the threshold below which you don't want to experiment. And you see that if you have failures first, successes first, you experiment 3 times before you stop. And so you generate data for 3 years. If you have the failures first, which is the graph on the right, so this is exactly exactly the same situation except for the order. Exactly same situation, except for the order. I've put 2 successes, 2 failures. On the left, 2 successes first, 2 failures last. And on the right, 2 identical failures first and 2 identical successes left. And you see that the beliefs converge very quickly to very low beliefs where you don't want to experiment if you have a failure first. So you're not going to experiment if you have a failure first, which is something that is totally uncontrollable. Insurers cannot do anything about this, farmers cannot do anything about it, and even a good DSS is going to fail sometimes. So this is really a randomness, pure randomness in this process, which means that in some cases, you can have insurance, which is a very helpful tool in allowing experimentation. It's going to be super effective. And and maybe that's the case in Veneto, and in other contexts, it's going not to work, and this will not be anyone's fault except for the conditions that made us experiment a failure too early, and people are going to react. It's not overreaction because it's based in the beginning, it's very rational, but they're going to react very negatively. Okay. So I think I can skip this because this is this experiment we did in Cicciac and Buzet that Marianne mentioned and Mark as well. Just one thing, it was interesting for us to see that it reflected this learning thing. That is, the cooperatives didn't want to have a deductible in the first year, and then they accepted a deductible because there were successes. We had 3 successes first, and then 1 failure. We were in a context with 3 successes and a failure. And the insurer, which was Groupama, I don't know if I should have said this, had computed a minimum premium which was nearly twice at the beginning compared to the one it decided to set in the last year. So there was learning that the DSS was good, but it was good, it worked, because we had failed. Okay, and then we had a failure in 2022. And I'm nearly done. If I have the time, I would like to just mention a few things, which is that if my farmers, in addition, are loss-averse or regret-averse, insurance is all the more beneficial. Because, of course, they're going to treat losses as weighing much more. Okay. Regret aversion is particularly complicated with learning because if you don't want to regret, you don't want to learn. You want to avoid learning just in case you learn something that would make you experience regret. But insurance would help. Index insurance, it has been mentioned, it helps with moral hazard because it deals with something that is not directly under the... Oh, sorry, I'm going to skip this. Just it doesn't help much with our problem here, which is giving incentives to experiment. Because whatever the index, you might have experimented or not, you might have followed the recommendations or not, and you're going to have your produce that you can sell, and you can be indemnified even if you have good results. So it rather pushes you towards not following the DSS, playing safe, and spraying, just in case. You see, because the index is not going to say if you sprayed or not. So it's not a very obvious solution to our problem here, which is something we can discuss. Collective insurance contract is something I would have liked, I don't have time, but I would have liked to suggest as something that might be helpful, probably more in developing economies, this idea that, okay, one farmer doesn't want to experiment. Mutual insurance funds have limitations because the risks tend to be common, and also they don't have access to the same reinsurance and optimizing facilities as professional insurers. Individual insurance is not often very profitable and doesn't necessarily give you incentives to innovate, especially if innovation means taking the risk of not having produce and not having produce that your buyers are expecting you to have. So what I like in future work to model is this, the fact that, and this has been said to us by quite a number of wine growers, it's not the same thing to have money or to have grapes that you can sell for reputation and for buyer contracting agreements, etc., etc. So it's not equivalent. If you have a group that decides to experiment, one of them can experiment, and they can all share the produce they have, and they can share the financial indemnity. In that way, they are limiting the loss that is due to not having produce. Okay, they're spreading not only the financial risk, but also the production risk. And it looks from the equations that it could work. Of course, it's a model, so I would be very interested in your feedback whether this could be something interesting or not. Not sure about that. Not seen it tried somewhere. Thanks.
Thank you.